if you remember back to the start of the term, we basically had the electromagnetic spectrum, and there was basically the low energy, high energy, and infrared was, IR was somewhere in here. And this dealt with, and then there was low energy, and NMR was over here. This was with the radio waves. So with NMR, of course, we are changing the spin of a nuclei. In infrared, we were dealing with the bending and stretching energy level. So molecules would bend, so the bond angle would change, or they would stretch, so the bond length would be compressed or get longer, what have you. And with UVVis, it's over here, UVVis. So, and the visible spectrum would come in between the infrared and the ultraviolet. And this is dealing with electronic transitions. So we are taking ground state and we are exciting it to the excited state. Ground state, so energy. So we are dealing with this type of stuff. So this is electronic energy levels. So so we are going to be moving electrons from, say, a sigma orbital to a sigma star, or a pi orbital to a pi star, or a non-bonding orbital, non-bonding electrons, so lone pairs, to, say, a pi star. So we're talking about electronic energy level transitions here. So these are, out of all of the three of these are the basically the highest energy that we're talking about. Basically that's, so we're dealing, yeah, I guess the key point is that we're dealing with electronic transitions here. Are you seeing the screen?
Yeah.
Okay. Okay, so now I don't know, what do? Do I just, so I'm recording all of this, so I guess I just clear the diagrams. Yeah. So when we're talking about electrons being promoted, typically what we're going to see is electrons in the highest occupied molecular orbital being moved to the lowest unoccupied molecular orbital. So these are, most of the time, these are going to be homo-LUMO transitions. And what's interesting is that for this, in organic chemistry, for like for most organic functional groups, they actually, most of them fall outside the range of that we're looking at. So the range is basically between 190 nanometers and 800 nanometers. And so most of them actually are outside of these, it's outside this range. So you'll see that when you're using transition metals and things like this, like a lot of inorganic chemistry, UV visible is used a lot more than organic chemistry. But it's one of those. It's part of the electromagnetic spectrum, and so we cover it a little bit. There are some like exceptions to this. Some molecules will be quite visible, and it's just one of those. It's just one of those things. But for most functional groups, they actually fall outside this range. But that's just one of the way it is. So yeah, so it's electrons that are being promoted. So in the infrared, it's bonds that were moving. And in NMR, it was the nuclei just doing a spin flip, which was responsible. But this one's actually moving electrons. So for the highest occupied molecular orbital, if we were to draw a, let's see, HOMO and LUMO. So if we had a little energy diagram here, just in broad terms, if we had to sort like sigma electrons versus pi electrons versus non-bonding electrons, where would you put these on this graph, like A, B, and C? Where would the sigma be? Where would the B be? Where would the C be? Like what's responsible for, like, where would the sigma be, or the pi, or the non-bonding? So N is non-bonding. What would be your intuition? Which one would be the lowest? Right, sigma. So sigma would be the lowest. And the next one's probably the one which is a bit more slightly complicated. Which one would be B and which one would be C? So typically the highest are the non-bonding, and then the pi would be somewhere in the middle. And if we were looking at the LUMOS levels, so the lowest unoccupied, these tend to be sigma star orbitals and p star orbitals. Which would be lower, the sigma star or the pi star? Right, pi star. So the pi star would be the lowest, and the sigma star would be the highest. So good. Now, if we are looking at various functional groups, so the what have I done here? What's wrong? What am I doing? Erase. Sigma star. Right. Okay. So the lowest energy for the LUMO would be sigma star to pi star. So if we were doing, so the transition, I've sort of done this upside down. The LUMO should be at the top and the HOMO should be at the bottom. But if, so for an alkane, the transition that we would see would be from, because an alkane's only got, there's no double bonds in there. This would be a transition from the sigma to the sigma star. Our functional group was an alkane. If our, and this would, out of all of the energy differences, like if this, make a little graph here, this is increasing energy. This would be the highest, energy, because, let me erase this. Pi star. So this energy difference here, this is just energy. This would be the largest gap, right? Sigma all the way up to the sigma star. The shortest gap would be from a non-bonding electron to a pi star. So this would be the shortest, n to pi star. And the group which would have this type of transition, so we need a lone pair and we need a pi bond of some type. And so the most obvious one would be carbonyls, because a carbonyl has got lone pairs and it's got a pi bond. So this would be the lowest energy transition. The next lowest energy would be n to sigma star. And so here again, we need non-bonding electrons, but we don't have a pi bond. So this would be things like alcohols, basically anything with an oxygen and a nitrogen and a sigma bond. So then we could get up to the pi to pi star. And this could be alkenes. This could be carbonyls. This could be alkynes, I guess. All of these types of things. So anything with a pi bond, and it's going to have a pi star. And then I guess the last one would be the sigma to pi star. And this sort of transition would be common in, I guess we could see this in a carbonyl as well. Yeah. So we'll see that carbonyls actually have quite a few transitions, possible transitions. One of the things which is interesting is that some of these transitions are forbidden. Okay, so let's see here. Okay, I guess I'll clear this page. All right, so next point. This is helpful. Not all transitions are observed. There are what we would call selection rules for this. We won't get into this too much. Did Dr. Yan talk about this at all in the group theory class?
I know he talked about it in inorganic too.
Okay, so basically this is all a repeat?
Yeah, for me at least, because I did inorganic already.
No.
I haven't done that yet.
Okay, well, then there we go. So that, okay, that's well, then this will be at least. So there are certain transitions that are not observed. There's certain selection rules that that you have to apply. So there are such things as called like forbidden transitions. And the funny thing is that although they're technically supposed to be forbidden, sometimes you still see them. It's just that that they are far weaker than the allowed ones. And the most common forbidden transition that is sometimes seen is the N to pi star transition. So this would have been the one we had at the lowest energy of the that little graph in the last page. So this is the most forbidden one that can be observed. So I guess we should basically talk about what the spectra looks like. So in UV spectra, I guess. So if you do something, if you run one of these spectras on an atom, what you are going to see is very sharp lines, I guess. And so it's basically quantized really nicely. So it's going to be sharp. But with molecules, which is what we're dealing with, this can be it won't be sharp at all. It's going to be what I guess you'd have a very broad spectra, very broad. Now, the reason for this is that when you've got a molecule here, okay, so let's look at energy. So this is the ground state, and this can be the excited state. So in an atom, you've got the ground state can be excited to the excited state, and end of story, you get this delta E equals HV. Very straightforward and all that sort of stuff. But when we've got molecules, there are the smaller energy levels that are right above here, right? For basically vibrational modes, and even so there's vibrational, rotational, transitional, all these little smaller energy levels. I think you probably do this in phys chem at some stage. So and so if you can get a transition from the ground state to sort of there, or one of these vibrational modes to here. And so because these get smaller and smaller and smaller when you've got the rotation and the translational stuff, then you end up getting, instead of having a sharp peak, you end up getting broad peaks because of all of the smaller, because the energy isn't one defined packet. There's a whole bunch of things that'll fit into that area. So So the vibrational and the translational modes are even smaller than the vibrational ones. So for the spectra, you tend to get they tend to be very broad, which is interesting. Okay, so there is a so there is basically there's a law, the Beer-Lambert law. So A equals the log of okay, Kat, I'm gonna have to put you outside. So A here is absorbance. So your molecule it receives the appropriate amount of energy, and that's where the absorbance takes place. So this is the light or the radiation entering your cell. And this is the light leaving the cell. So if you've got your little sample dissolved in some solution cell, this would be I0 and this would be I. So if the molecule is absorbing this, if it has the appropriate sort of energy, then it's just very similar to infrared. And so, and then here are some other factors. This is what we call this E is the molar absorptivity. This would be the concentration. And L is basically will be the path length of this little cell here. So there's this neat little law which you can use to, and this basically works it's basically rigorously obeyed under a lot of, this should be an M here, Lambert. It's basically obeyed pretty rigorously under a number of different situations. The times when it's not obeyed is if there's some sort of equilibrium process taking place, if there are some, and this could be if there's some sort of, because complexes, I guess would be the better word. So it's your sample's dissolved in the solvent. If your solvent forms some sort of complex, then this can mess up this law a little bit. For fluorescent compounds, it doesn't really work. And if there is, equilibrium seems to be the big stumbling block. But for most of the stuff, it's pretty rigorously obeyed. So the ranges of absorptivity can be like basically 0 to 10 to the 6th. And so anything greater than 10 to the 4, we would call this high intensity. And anything less than 10 to the 3 we would call low intensity. And forbidden transitions are, 0 to, would be in the low intensity range, like 0 to 1,000 or whatever it would be. Okay, so for our instrument, we sort of, what we need for our instrument, we basically need 3 things, and I bet you can predict what they are. Based upon infrared, our infrared instrument. In fact, this is a good question for comparing and contrasting an infrared spectrometer with a UV visible. What would be the first thing we would need? Okay, what would be the last thing we would need? And it starts with D.
Detector.
Right, yeah, detector. So this could be a photomultiplier or a photodiode tube. So basically, it's going to be recording the different wavelengths of the of light. So in our old infrared, we had a dispersion, or we had a Fourier transform. And the difference between the dispersion and the Fourier transform for infrared was basically what? One of them had a lot more moving parts. One of them had still some moving parts, but it was easier, so to speak. So there's my, this is the sample. This is the reference. Here's my quickly drawn IR dispersion spectrometer, and here is my quickly drawn and this, we need a reflecting thing. Actually, this goes here, and then we had a mirror, right? No, it goes there. Then we had our detector. This is our Fourier transform. So in the dispersion infrared, we had this beam chop. We had a reference cell and a sample cell. We had a beam chopper which would cut the beam, and then the light would alternate between going through the reference or going through the sample, and it would hit this thing, whatever this was, which would deflect, I suppose, a certain wavelength of light hit the detector. So you'd scan from one wavelength, you'd scan to a different wavelength. Do we remember that? Whereas with the Fourier transform, all wavelengths were at the same time. Based upon the moving mirrors, you get the interferogram, and then the detector, it would detect everything, and then you'd use a computer to give the entire spectra from all of the like low wavelength to high wavelength. So the instrumentation for a UVVis is quite similar to all of this. So one of the things that we need, of course, is the light source at the start. And so for the ultraviolet, we would use a deuterium lamp. And for the visible, the common one, which is used, is tungsten. And the second part, which we have in here, would be the mono, like, so the beam chopper, the diffraction grating, all of that bit together is the monochromator. So this would be the diffraction grating and the little opening, which only allow a certain wavelengths through at a given time. And of course, this instrumentation changed as well with Fourier transform. So you can use a photodiode array so you don't need this diffraction gradient anymore, and you can basically just been an upgrade to that as well. So so the instrumentation is very similar to the two, but you still need a light source. You need a monochromator and the detector. And with improvements in instrumentation, you basically can have a Fourier transform UVVis as well. And so the way that this is essentially plotted is on one axis, you've got the x-axis, you've got your wavelength in nanometers. And in the other, you've got the log of epsilon, or sometimes it's just epsilon, but usually it's the log. And it's basically an absorbance versus wavelength sort of graph. And it would be something like this. It's kind of drawn not very great here. Let's erase some stuff. Oops. And at various places, you might have a maximum wavelength, and this would be recorded in such a fashion. So you could have a maximum at say 230, and this log of epsilon would be say 4.2, something like that. And then, yeah, so that's basically what it looks like. There are some important sort of considerations to keep in mind. First is that you don't want to use a solvent in your solution cell, which is going to interfere with any of the radiation. So the solvent is sort of the solvent's important. So for example, water's got a maximum at 190 nanometers, which would be the lower end of and hexanes is at like 201. So these are both right at the lower end. So you have to choose a solvent which isn't going to necessarily interfere with, it's going to absorb in the area that you want it to absorb in. You can get, if you've got, say a solvent, whoops, question. You could, yes. So the question is, can you use these? Yes. If you're looking for something in a completely different range, yes, you could. I think you probably, when you were doing, because I remember in organic, the little UV visible spectrometer is right beside the infrared in the lab, and often Dr. Yan brings everybody in there to use it to run samples in. What solvent did you use when you used to run them? Anyone who's taken that class.
I can't remember it. I'd have to like look into it, but I feel like it might have been hexane.
Right. So in the so these are really, this is at the low end. So if this goes between 190 and 800, this is where we're looking at. So these are both right at this level. So you're not going to miss, you're like, they're not going to cover too much other stuff. So some other, I don't actually have a, if you look at all the various sample bottles for solvents, particularly if you're using them for HPLC, they will usually list the lambda max on them. And it's, I can't remember any offhand besides these two, but these are in the lower range. So it would be safe for anything which absorbs up here. They would be fine. But you could see that things like acetone or say ethyl acetate, compounds that have, or even benzene, for example, those would have transitions that would be right in the middle of this, because they've got, like, for example, acetone could have all of the various transitions: a sigma to pi star, a pi to pi star, an n to pi star. It could have all of these various, some of them would be forbidden, but you have all of these transitions which could get in the way. So these two, I think, are, because they're at the lower end, they are good solvents to use. Now, in organic, we just talked about aprotic solvents versus protic solvents. And let's pretend that if you are a, like, if you are the molecule being, we're running a UVVis spectra on you, and you can, let's pretend that you can hydrogen bond. It's too bad I erased the four. I should have used the OneNote to draw this sort of stuff. But what typically, like, protic solvents and aprotic solvents can have different sort of UV spectra. Particularly, protic solvents tend to be broader because of hydrogen bonding. So if the solute can hydrogen bond and the solvent itself can hydrogen bond, then when we're looking at the energy levels between the two sides, and we've got all those vibrational energy levels and the translational energy levels, the hydrogen bonding, so the solute and the solvent can form a complex, and the transitions, these little energy levels become more important. But if you use an aprotic solvent and hydrogen bonding is basically diminished, then sometimes some of these peaks could appear to be sharper as opposed to very broad. So it's it's not going to be like an atomic spectra. There's still going to be some broadness to it, but you can see it could get pointier, I guess is a very non-scientific way of speaking about it. And then there is some other things which can be important as well. Polar solvents can shift N to pi star to shorter wavelengths, and pi to pi star to longer wavelengths. We'll talk about that a little bit later on. Now, where are we? Okay, so what we'll do on next class, because I guess next class is Thursday. Next class will be the last class we actually discuss anything new. We will talk about basically the chromophores of the various functional groups, which we've sort of talked about. So a chromophore is basically the group of atoms which is going to be responsible for the transition. And we'll basically give a range of where these, like what wavelengths these would come out in. So that'll help us out a bit. And then there's some substituents on chromophores which can give the chromophore a red shift or a blue shift, or they could increase the intensity of it or decrease the intensity of it. So these are, there's some like little names for, like a red shift would be a bathochromic shift. We'll talk a bit about that. But it's useful to get some of to give everyone a sense of where, like what wavelength certain things show up at. In organic chemistry, the molecules that which are useful for UV visible, are things that are highly conjugated. So conjugated systems, the gap between the HOMO and the LUMO gets shorter and shorter and shorter. And so some of them make, like most organic molecules are white, right? There's maybe a little bit of yellow. Like it's kind of boring when you do inorganic chemistry, you make stuff which is blue and purple and all these sorts of fun colors. But with organic chemistry, it's usually, oh, I got a white solid or a non-colored solid. Not particularly interesting. But when you conjugate systems, then you can start to see some that gap becomes smaller and smaller and smaller. So some of the dyes, you can actually make some really bright colored organic compounds, but these tend to be super conjugated systems. So that's what we're going to talk about. And so that's basically, I guess, where we're going to go. This would be really, yeah, so that's what we'll do on Thursday. So there's really, like, if we're gonna use this in a like in an exam or something like that, I think for the final exam, what we're gonna focus on is the theory around NMR and not this. So if you're worried about like keeping any of this sort of stuff in your brain, don't worry about it too much. The key point though will be if something's a conjugated system, I could give you a hint for that on a test by saying this shows some UV visible, you know, a strong absorption at blah, blah, blah. And that will just be a hint that, oh, okay, well, there's some conjugation here. But we could also figure that out just through our infrared, right? Because conjugated will decrease the wave number of carbonyl or whatever it might be. But we'll just go through some of the stuff next class about where certain functional groups show up and how to get a bathochromic shift, how to a blue shift or a red shift and increase the intensity, that sort of stuff. And then that'll be it. And then next Tuesday it can just be review. And what I'll do is I'll give everybody a whole bunch, just like sort of I did with the mass spec. I can give you a big long list of all the theory questions I asked in NMR over the last 4 years. And as you saw in the last midterm, I basically chose all my questions from that. So it'll be a good way to study, I guess. Any questions at all? Sorry, I'm going over our time. All right, well then, I hope everyone has a good day. I'll see everybody on Thursday.
Hey, have a good day, Dr. Hill.
You bet.